Docker containers. Docker containers are lightweight, standalone, and executable environments that package an application and its dependencies, allowing it to run consistently across different environments. Containers provide a way to isolate applications and their processes, ensuring that they can operate without interfering with each other or the host system. Here's a more detailed explanation of Docker containers. Isolation and consistency. Containers use Linux kernel features like namespaces and cgroups to provide process-level isolation. Each container has its own isolated file system, network, and process space. This isolation ensures that processes within a container are isolated from processes in other containers and from the host system. Portability. Docker containers are portable across different environments. The container encapsulates the application code, runtime, libraries, and configurations. This means that a containerized application will run the same way on a developer's laptop, a testing server, or a production cluster. Lightweight. Containers share the host system's operating system kernel, which makes them much more lightweight than traditional virtual machines. Containers require fewer resources and start quickly compared to VMs. Ephemeral nature. Containers are designed to be ephemeral, meaning they can be started, stopped, and deleted without affecting the host system or other containers. This characteristic makes containers ideal for scalable and dynamic applications. Images as blueprints. Containers are created from Docker images. An image is a read-only template that contains everything needed to run an application, including the code, runtime, libraries, and environment variables. Containers add a thin, writable layer on top of the image, allowing temporary modifications. Statelessness and data persistence. Containers are designed to be stateless, meaning they don't store critical data within the container itself. Data that needs to persist should be stored in volumes or external databases. This design philosophy allows for easy scaling and replacement of containers. Networking. Docker containers can be connected to various network types, including bridge networks, host networks, and overlay networks. Docker enables containers to communicate with each other and with the outside world through network ports. Lifecycle management. Containers have a clear lifecycle. They are created, started, stopped, and removed. Docker provides commands and APIs for managing these lifecycle operations, making it easy to automate container management. Orchestration and scaling. Docker containers can be managed at scale using orchestration tools like Docker Swarm and Kubernetes. These tools enable deployment, scaling, and load balancing of containers across multiple hosts. Creating, running, and managing Docker containers. Creating, running, and managing Docker containers is a crucial aspect of using Docker for application deployment and development. Here's a step-by-step guide on how to perform these tasks. Pull or build an image. To create a container, you need an image. You can pull an existing image from a registry, e.g., Docker Hub, or build your own image using a Docker file. Create a container. Use the Docker run command to create and run a new container from an image. This command creates a detached container named myContainer from the Nginx image, maps port 8080 on the host to port 80 in the container, and runs it in the background. View running containers. Use the Docker ps command to see a list of running containers. View all containers, running and stopped. To see a list of all containers, both running and stopped, use the Docker ps command. Stopping containers. Use the docker stop command to stop a running container. Starting stopped containers. To start a stopped container, use the docker start command. Restarting containers. To restart a running or stopped container, use the docker restart command. Removing containers. To remove a stopped container, use the docker room command. Logs and executing commands. Use the docker logs command to view logs of a container. Use the docker exec command to execute commands inside a running container. Port mapping and container interaction. Port mapping, also known as port forwarding, allows you to expose a network port from a container to the host system or to other containers. This is essential for allowing external communication with applications running inside Docker containers. When you run a container, you can use the P or publish option with the docker run command to map a port on the host system to a port in the container. In this example, a container based on the Nginx image is created, and port 80 inside the container is mapped to port 8080 on the host system. This means you can access the web server running in the container by navigating to http://localhost port 8080 in your web browser. Container interaction. Docker containers can interact with each other in various ways, including networking and communication. Containers can communicate either on the same host or across multiple hosts in a Docker swarm or Kubernetes cluster. Here are a few common ways containers interact. Network communication. Containers can communicate over the network using IP addresses, DNS names, and port mappings. Containers on the same network can communicate using container names as DNS names. Linking containers. Legacy. In the past, Docker used container linking to enable communication between containers. Container linking is considered legacy, and modern approaches like Docker networks are preferred. Docker networks. Docker networks provide a more controlled and flexible way for containers to communicate. You can create custom Docker networks and attach containers to them. Containers in the same network can communicate using their container names as DNS names. Examples of Docker network types include bridge networks, host networks, and overlay networks, for multi-host communication. Container-to-container communication. You can use the docker exec command to run commands inside a running container, allowing you to interact with the container's file system and processes. For example, docker exec it mycontainer bin bash will start an interactive shell inside the mycontainer container. Inter-container data sharing. Containers can share data using volumes, which are external directories mounted into containers. Volumes allow persistent data to be shared between containers even when containers are stopped or removed. Orchestration platforms, e.g., Kubernetes, Docker Swarm. Orchestration platforms enable you to manage and scale containerized applications across multiple hosts. They provide more advanced networking and communication features, load balancing, and service discovery. By understanding port mapping and container interaction, you can design and deploy containerized applications that work seamlessly together, communicate efficiently, and leverage the benefits of Docker's isolation and portability. Thanks for watching.